Hi, everyone. Okay, I'd like to introduce the lab on Compton scattering. You know, we started this course talking about special relativity, and then we followed that by talking about the photon theory of light. So it's neat to do an experiment now that tests both special relativity and the photon theory of light. This is also the only experiment where we'll get to use some sort of particle techniques, where we're counting particles instead of measuring wavelengths or things like that. So that's interesting too. The apparatus will look rather different than the other experiments. I'd like to use two videos to introduce this experiment. The first one, this one, will introduce the theory, and then there's another one that will look at the apparatus, okay? Maybe we'll need two videos for that, but they'll each be short. Anyway, let's get started and talk about the theory. Hang on. Okay, the theory of Compton scattering is based on two results. The first is the photon theory of light, that photons have an energy associated with their frequency. And the second is the relativistic expression for energy and momentum, which says that if I have an object, maybe an electron, that the energy of the electron can be written in terms of its momentum and its rest energy in this way. Okay, both expressions which should be familiar to us from earlier in the course. Okay, in Compton scattering, we have a photon, like a gamma ray, that scatters off of an electron. The electron is taken to be at rest. So here's how the experiment is set up. We imagine our electron here, and then we have a photon with energy E sub gamma, which is instant. After the photon strikes the electron might recoil. And the photon will also be scattered. Perhaps scattered through some angle theta. And interestingly, its energy will change. Okay, that's the process that we want to describe. All right. So to do this, we need to think about this process as sort of a particle collision and conserve energy and momentum. So let's take a look at this process. And the goal of our analysis will be to find the energy of the scattered gamma ray, E prime. Okay? All right. Actually, we treated this problem in class and maybe on a homework assignment some time ago. Only in the homework assignment, we made an assumption that the scattering angle was 180 degrees. We're not going to make that assumption now. We'll just do it in general, okay? So when we set this problem up, first, let's make sure we understand our notation. In terms of gamma rays, we're interested in the incident gamma ray, which has some energy, E, which we'll write as its momentum times the speed of light. Now, it would make sense to call this E gamma and P gamma, but I'm going to try to keep our notation simple. So when I write an energy or a momentum without any subscript, it's the gamma rays. After the scattering, we can say that E prime, the energy of the scattered gamma ray, is equal to its momentum times C, P prime times C. Then we have the electron. Initially, the electron is at rest. So the energy of the electron, now we're going to use a subscript, is just equal to its mass times speed of light squared. but the final energy will be determined by its rest energy and its momentum. Okay? And using the formula we wrote up above, we can write this as PEC squared plus MC squared for the electron. Okay? Oops. There we are. So initial and final energy and momentum for the gamma rays and the electron. Okay, just introducing our notation. So now let's look at our problem here and write down expressions that define energy conservation and momentum conservation. First, energy conservation. Okay, so we know that the initial energy, which is the energy of the gamma plus the initial energy of the electron, has to equal final energy, which is the energy of the scattered gamma ray plus the energy of the electron after scattering. Okay, and we'll just solve this for the energy of the electron after scattering. Like so. And then I'm going to manipulate this into a form that's going to be useful in a couple of minutes. To do that, I'm going to square both sides. Okay? And then now we can use the relationship we wrote down a moment ago. The square of the electron energy is its momentum times the speed of light squared plus mc squared. And this is equal to E minus E prime plus the initial energy of the electron, which was mc squared as well. And so we have P sub E C squared is equal to this. There we go. So this is equation 1, and it's just energy conservation, only I've rewritten it in a particular way. I've written it in terms of the momentum of the scattered electron. Okay? Perfect. The next step is to use momentum conservation. So here, we know that the initial momentum, which was the momentum of the photon, initial photon, is equal to the, since the initial momentum of the electron was 0, is equal to the momentum of the scattered photon, plus the momentum of the electron after scattering. Okay? Or PE is equal to P minus P prime. So these refer to the energies of the gamma ray. Okay? Now, I'm going to square this because I want to make it look as much like equation 1 as I can. We're going to use a trick, okay? Okay, so let's square both sides. Then I have PE dot PE on the left side is equal to P minus P prime dot P minus P prime. Notice, by the way, that momentum is a vector. So this is all these are all vector equations here. Well, PE dot PE is just magnitude of the electron momentum squared. And then on the right-hand side, we have P dot P plus P prime dot P prime minus 2 P dot P prime. Okay? And of course, this is equal to the momentum of the initial photon squared plus the momentum of the scattered photon squared minus 2 times the momenta of the photons of P times P prime, the momenta of the two photons, the magnitude of the momenta, times cosine of the angle between them. Okay? This factor of cosine theta, of course, comes from the dot product from two vectors which don't necessarily point in the same direction, P and P prime. Now we're going to multiply both sides by c squared, and we have PEC squared is equal to PC squared plus P prime C squared minus 2 PC P prime C times cosine theta. And we're doing that because the terms on the right are then the energies of the photon. So this is the initial energy of the photon squared plus the initial energy of the scattered, so the energy of the scattered photon squared minus twice E prime cosine theta. And on the left-hand side, we have PEC squared. Okay? And this is our second equation. Oops, let me move that up. There we go. All right. Here, let's just write those next to each other. 1 second. All right, well, we have these two equations. Equation 1 represents energy conservation. That's where it came from. And equation 2 came from momentum conservation. Now look, in equation 1, we've manipulated it into equation for P sub B C squared. And likewise for equation 2. That means that the right-hand side of equation 1 is also equal to the right-hand side of equation 2. So let's set them equal to each other and then see what we have. When we do that, we'll have eliminated the electron momentum from the equation. And what's left will be much simpler. Okay? Great. So when we do this, what we have is starting with equation 2, excuse me. There we are. We have E squared plus E prime squared minus 2E prime cosine theta. And that has to equal this. E minus E prime plus MC squared, quantity squared, minus MC squared, quantity squared itself. Here, let's expand the right-hand side of that equation, see what we have. So expanding this term here that's squared, we have E squared plus E prime squared plus MC squared minus 2E prime minus 2E prime MC squared, and then plus 2E times MC squared without the prime. Okay? Ooh, very good. Oh, and then we have this term, minus MC squared. Great. Now look, we can cancel a term here. This cancels with that. All right. And then between the two equations, we can see that this cancels this, and this cancels that. Okay? Very good. Here, let's just rewrite what we have left. We have minus 2e prime cosine theta is equal to minus 2e prime minus 2e prime mc squared plus 2e times mc squared. Okay. Now, here we have an equation. It's still a little messy looking, but in this equation, the only thing that's unknown is E prime, okay? We assume we know what the energy of the initial photon is, and we assume that we can set the scattering angle theta, okay? So let's solve this equation for E prime, all right? Before we do that, here, let's just cancel out all the negative signs. Maybe we have to do this in white, so you can see it here. Okay, and we could also cancel out the factors of 2 that you see everywhere. Okay, so now let's isolate the term that has just E in it. So we have EMC squared, that was this term here. And that's equal to, and all the other terms have E prime in them. E prime times 2E plus 2mc squared, and then minus this term here, 2e cosine theta. Okay? So it's clear that E prime is equal to E times mc squared divided by 2. Oh, I'm sorry. I wrote those 2's over again, but we'd already canceled them out. Let me go get rid of them. There we are. Very good. E plus mc squared minus E cosine theta. Okay? Very good. Now let's divide top and bottom by mc squared, and we'll be done. E prime is equal to the initial photon energy divided by E over mc squared times 1 minus cosine theta. And that's it. We're all set. Let's put a box around this. And we're done. So what we've done here is to find a formula for the energy of the scattered gamma ray in terms of the energy of the initial gamma ray, the mass energy of the electron, and the scattering angle theta. Okay? Very good. Oh, and I see I left one term out. It should be 1 plus all of that. All right, that's our expression for Compton scattering, here written in terms of the energies of the particles. And it's interesting behavior. It's not so obvious, right, that this would be the right answer. So if we do a test and we find that this equation holds, it really is a strong proof that the relativistic expression for energy that links energy and momentum must be right.